Going to talk about state discrimination. If you recall the problem of state discrimination, you have Alice here. That sounds like a state, which is like row x. So she has the states row x, and so she sends it with a probability like which is px of row x to Bob. And Bob, in order to measure, like to guess what is x, he measures a POVM which is MYY on it, and on the states he receive. Like, so he like to have MYY of like of the trace of PX MX, like, yeah, M1Y of the sum of PX as a trace of row x MX. And so by maximizing the probability, like if he maximizes this, he gets correctly over all possible POVM, he obtains the optimal guessing probability. So this is like the optimal guessing probability. And we all, if you know about it, like before convex optimization, you can show like that when Alice sends one of two states, like if Alice has only like, for example, if only two cases, like if only two states, so row 1 and row 0, like x equals 0, x equals 1, then we can see, like, thanks to the Oliver-Ohlstrom theorem, that the optimal probability of guessing, the optimal guessing probability is like 1/2 plus 1/2 of P0 0 minus P1 row 1. And so thanks to this, like you know this, like thanks to the Oliver-Ohlstrom theorem, and yeah, but so here you see it's only for two states, only two. But what if we have like a fun, like to discriminate like between not only two states but what about n states, you know, as many states as you want. So that's where not this will not be sufficient. Not sufficient, and you'll need convex optimization. So yeah, we can write like this, and we can write down the optimization over measurements. We have then like convex optimization is like this. You just have the probability, like if we retake literally the same, the optimal guessing probability can be defined as the max of my phi of the sum of x px. So let's trace of for x into x as earlier, like you have the property px takes over the trace over it with the p of m, and you respect the constraints of the p of m because the sum of the p of m should be um, equal to identity and semi-definite positive. As you see, it's just the formula. It's an SDP, like it's literally the form of an SDP, and so we can apply a context optimization on it. Uh, we can apply the we can apply like the convex optimization, and more especially like the semi-definite programming with the Lagrangian methods. With Lagrangian on it. So yeah, we can like we can, we can like we can find like the optimal measurements for discrimination. At least we can guarantee like we have a we have an efficient algorithms for it. So yeah,